Hello everybody. In this class, we start discussing analog to digital conversion. So, in this we shall cover these concepts. So, simultaneous conversion and use of this method for flash converter type analog to digital converter ADC, and then we shall discuss counter based conversion and also continuous conversion. Okay. So, these are the three things that we shall take up in today's class. So, first we try to understand the concept of simultaneous conversion. Okay. So, for which we look at one small example, what you see in the left hand side. So, there is an analog input voltage which is restricted to in the range 0 to V volt. Let us consider it that way. Okay. And this is going in parallel to three comparator inputs. There are three comparator inputs, three comparators C1, C2 and C3, right. And each of these comparator has got three different kind of reference voltages. Okay. So, for first it is V by 4 plus V by 4, second plus V by 2 and third plus 3 V by 4. Is it fine? Right. So, what will be the output C3, C2, C1 for different voltage ranges of the analog input voltage. Okay. So, that is seen in this part of the truth table that you can see where this yellow box is the one, yellow box 1 is the one where you can see how the input and output of this particular block is related. Okay. So, when the input is 0 to plus V by 4, okay, in this range. So, what is happening? For each of these cases, this input is less than the threshold voltage or the reference voltage that is set for each of the comparator, is not it? So, for each of the comparator, then the output will be 0. So, this is the case. Is it clear? Now, when the input is from plus V by 4 to plus V by 2, okay. So, then what happens? So, it is for this particular comparator, it is above the threshold. Is it clear? So, this comparator will give you a output 1, C1 will be 1. For rest of the cases, it is below threshold. This is V by, this will, this threshold is V by 2, it is less than V by 2. And this is 3 by V by 4, that is also, this is also less than 3 by V by 4. Okay. So, this is the case that you can see. When it is in this range plus V by 2 to 3 V by 4, then what happens? Of course, it is more than this threshold voltage and also more than this threshold or reference voltage, right. So, C1 and C2 will be high at that time, okay, and C3 is 0. Is it fine? And what happens when it goes to 3 Vb by 4 to plus V this in this range, right. So, the analog input voltage is more than the reference voltage for each of the comparator, right. So, all of them will be giving a output 1 as you can see in this particular case. Is it clear? Right. So, with three comparators we can see 4 ranges are mapped in this manner for the analog input voltage at the output of the comparator, right. Now, with this kind of thing C3, C2, C1 that is there and 4 such ranges, if you want to encode it into digital, okay, this analog voltage into digital. So, these 4 ranges we know from what we have discussed before. So, 2 binary code is sufficient, right, because it is 4 ranges are there. So, one could be 0 0, another 0 1, another 1 0, another 1 1, right. So, instead of 3 outputs the way we have seen C3, C2, C1, we can have a scheme, an encoding scheme where C3, C2, C1 are the input, okay, and we get binary output where the scheme that we follow, that when all of them are 0, that is 0 to plus V by 4, right, the output will be 0 0, plus V by 4 to plus V by 2, C3, C2, C1 is 0, 0, 1, it will be 0, 1. Next one is 1, 0 and next one is 1, 1. This is one kind of mapping we can think of. Is it okay? So, how we can get this encoding done? So, to get this encoding done, we look at this particular relationship which is there within this bracket a bit closer. Okay? So, we can see that this output, okay, which is 2 to the power 1 output we are mentioning, just to give associated with the binary weight of that particular output, okay, in a binary number representation, the way we are done for DAC. So, similar thing we are thinking about ADC, right. So, this one is 1, whenever C2 is 1, you see C2 is 1 over here and 2 to the power 1 is 1 over here, C2 is 0 and this is 0. So, this is what we can identify, isn't it? So, from that we can write 2 to the power 1, this output is equal to C2, just like that. Okay. So, in the encoder within it, the logic circuit that we can have is just C2 is connected directly to the power 1. So, no other gates and nothing else is required. Is it fine? Okay. Now, for 2 to the power 0, this output, what we can see, this is, if C3 is 1, if C3 is 1, so C3 is 1, so this is 1. When C3 is 0, okay, it does not, I mean it is not something, I mean whenever it is becoming 1, it is becoming 1. C3 is 0 in these cases, we have to see some other relationship by which we have to figure out this particular one which is existing. Is it okay? In a sum of product method. So, this is the first thing that we can identify, and for this particular one we can see an unique combination when C2 is 0 and C1 is 1, which is occurring only once in this particular C3, C2, C1 combinations that is possible, okay, when you are doing a comparison like this of the analog input voltage and generating comparator outputs. Okay. So, at that time we can see that C2 is 0 and C1 is 1, the output is 1. So, we can write it this particular English statement in the form of a logic statement, logic relation C3 plus this is C2 prime C1. Is it fine? Okay. So, within this encoder what we have got, we understand. So, this is the analog input voltage, these are the comparator outputs. So, this will go to a logic block, right, and that is the encoder, and at the output there will be two outputs, two digital outputs. So, one analog input, two digital outputs, and we are getting this for particular a conversion, analog to digital conversion with 2 bits, 2-bit conversion. Is it fine? By simultaneous conversion method, right. Now, if we want a better resolution, so 3-bit conversion, okay. So, there will be 8 levels. So, let us see that kind of proposition, right. So, we are looking for 3-bit conversion. So, 8 levels. So, 8 levels, how many comparators will be required? As we have seen, for 4 levels, 3 comparators were required, because the first one was coming that all of them are below the threshold for each of the comparator, right. So, for 8 levels, right, 3-bit conversion, okay. So, we shall require 7 comparators. Is it fine? Right. So, 7 comparators will be generating output the way we have that particular table we can prepare, right, and from that this C1 to C7 output we can pass it through an encoder, okay. So, this is C1, this is C2 up to say C7, this we can pass through an encoder. So, 2 to the power 2, 2 to the power 1 and 2 to the power 0. So, this is your encoder, right. So, we can develop the logic for that, okay, the way we have seen the relationship in the previous case. So, similar thing we can find out, okay, and if we do, then what we shall see? We shall see that 2 to the power 2, that output can be directly taken as C4. The way we had seen earlier, 2 to the power 1 was directly taken for a 2-bit conversion case was taken from C2. So, similarly, it is taken from C4, okay. 2 to the power 1 in this case C6 plus that is OR C4 prime C2, and 2 to the power 0 will follow this relationship. So, this we can do, but just by drawing the table and then mapping it to the 3-bit relationship the way we had done for 2-bit representation for 4 level. So, 8 level, 7 comparator output and 3-bit mapping, okay, and this way we can get the encoding done. Is it fine? You understand this part? So, this can be extended to n-bit ADC, and we know the number of comparators required will be 2 to the power n minus 1. So, the number of comparators increases with the number of bits that you are using, okay. But this method is very fast because parallel comparison is being done, okay, and that is why when you make a ADC out of this, it is called flash converter, right. But the limitation of course is the number of comparators required, so for which power requirement is more, it becomes more expensive also. And regarding how fast it is, some numbers we shall see later when we discuss some other types of ADC, and then we can have a comparison, okay, right. And these reference voltages, these Vy8, Vy4, these reference voltages are required, okay. Earlier also you have seen Vy4, Vy2, 3 Vy4. So, this is obtained, can be obtained from precision voltage divider network, okay. So, that is how we can get it, right. And also we take note of that this encoding can be achieved by using priority encoder, which is available off the shelf as IC 9318, okay. And here whatever logic you see over here, so this is the logic, this logic block that you can see, right. And finally, the output are stored in a output register, so that you can use it subsequently. Is it fine? So, this is how flash converter based ADC can be achieved. Okay. Now, this number of comparators getting increased, and also we are not very comfortable with that, cost is increasing, power budget is increasing, right. So, can we think of something by which number of comparators requirement comes down, okay. So, one such scheme is counter based method, where the number of comparator required is only 1, okay. So, what was parallel before, now we have made sequential. So, of course, you can see, you can understand the trade off is with the time, okay. So, more time is required, right. So, let us see how it works, okay. So, what you see over here is a block, okay. So, there is a counter, right. So, this counter is initially reset, that is, it is initially at 0, okay, and then it increments, right. And when it increments, you have seen this kind of arrangement for a DAC. So, there is a level amplifier, there is a binary ladder. So, this ladder output, this analog output, that DAC that you get, which will be a step like this thing output. So, this output comes over here, and that is this is the comparator that I was talking about, right, and this is the analog input voltage, right. As counter value increases, this voltage will keep increasing, and whenever it exceeds the analog input voltage, the comparator output changes, right, and this comparator output goes to a gate and control circuit, which we shall see a little later, right, and that now inhibits the clocking to the counter, okay. So, whatever is the counter value is something which is related to the analog input voltage, and this counter value can be taken as the digital output, a converted value. Is it clear? Okay. So, one comparator which is comparing the value in each clock cycle till the DAC output of it, the counter output converted through a DAC. That is why we actually started discussion of this ADC DAC with DAC, because DAC is that concept, this ladder network is inherent in this type of ADC construction, okay, right. So, this is in this case, if the number is more, the analog voltage is more, and if you have got n bits, so you have to use all the bits, so it will go up to the 2 to the power n count. So, the maximum conversion time, okay, it can be up to 2 to the power n, right. So, if it is a 10 bit ADC we are talking about, okay, n bit 10 bit ADC and 1 megahertz clock is used here, right, then maximum conversion time is 2 to the power 10 into 1 microsecond. So, it is 1.024 millisecond, and if you take on average, because some numbers, some input will be high, some input will be low. So, it will be just average of these two, so about 0.512 millisecond. So, it is much slower, but number of converter requirement is less and the circuit is simpler. Okay. Now, let us see how the gate and control works for this particular circuit. Okay. So, this is the comparator, this is the analog voltage, this is the output of the ladder, which is effectively working like a DAC within an ADC, right, and this is the comparator output which is remaining low, right, when this reference voltage coming from the DAC, the counter output converted to analog output, right, through a DAC. Okay. So, this output is lower than the analog input voltage. So, at that time the comparator output is low. Okay. So, this comparator output is low, right, and what you see OS is a one shot. So, that is a 555 working in a monostable mode, right. So, when you start the conversion, so this is your start, right. So, immediately the counter is reset, and this particular control flip flop that you see, okay, is reset, okay, after it is set, it is after some time, okay, so that the clocking of the counter is staggered, is delayed by some amount. So, first it is ensured that the counter is reset by this, and then this one shot output is coming here. So, one shot output, it is becoming high 1, okay. So, this is 0. So, this output will become 1, right. After that it becomes 0. So, 0 0 means previous value will be returned. Is it fine? So, that when this is 0, this is remaining at 1 and this clock is coming. So, this clock will go to the counter, and counter will start increasing its value with every clocking. Okay. So, that is the clocking that is happening, right, and counter is increasing its value, and corresponding ladder output, the reference voltage, that is also getting increased. Okay. And this is the analog input voltage level. So, that is the dotted line you see, and whenever it exceeds it, what happens? This value becomes 1, right, this comparator output becomes 1. So, this is already 0, right. So, 1 and 0, now it becomes, this becomes 1 and this is 0. So, it becomes reset, okay, right. So, this is reset means clocking is now stopped. So, at the output of the AND gate, the clocking is stopped. Is it okay? And now, whatever is the value, that is the value related to the digitally coded value of the analog input. Is it fine? Now, in this counter based method, what we can see that it is starting from here. If the new start signal comes immediately after one conversion of the analog input voltage, and the analog input voltage is something like this, the one that you see over here, right. Now, it is starting, it is converting, then it is getting reset, right. Immediately we are considering that it is again next conversion starts immediately after it. So, next reset next count begins and it will go up to this level. So, for each of these cases you can see this axis is time. So, conversion time is different. Okay. So, this is what we can see from here, depending on the amplitude of the voltage, right, it takes more or less time, okay, with respect to one another, right. Now, when these particular digital codes are sent for reconstruction from say digital to analog, so reconstruction time has a certain value, right. Now, if it comes very close to one another like this particular case, right, so there could be issues with the reconstruction, right. And also the other thing that we see, that every time it starts from 0, counter starts from 0, okay, the requirement of the time getting increased, and maximum could be, as I said, 2 to the power n, depending on the magnitude of amplitude of this value, right. So, to overcome these sort of limitations in counter based method, what people have thought about a method of continuous conversion. Okay. So, in this say it has reached this value, so then it is not coming to 0 and again beginning from the 0, it is going from here to here. Okay. So, it is not coming to 0 and then again it is trying to reach this value, it is coming directly from here to here. Okay. So, this is the modification that is done. Okay. So, by which a speed up is achieved, right. And for this you can see here the counter is going up from the previous value, and here the counter has to come down, right. So, we need both up count and down count options within the circuit. Okay. Now, for this we employ a circuit which is of this nature, which is a upgrade of the counter based circuit that we had seen before. So, we had already seen this block before, okay, this block before, right. Now, this is the comparator. So, depending on the value, whether this analog input value is more or less, right, we are getting 0 or 1. So, we can convert it to up or down. Okay. So, up means it need to be increased, counter need to be increased, and down means counter need to be decreased, right. And this is now going to this control flip flops. Okay. These control flip flops, it works in this manner. So, every time the clock comes, this one shot, this mono shot, the mono shot that you had seen before, okay, it actually is resetting this particular flip flop. So, at every clock, this one shot resets the up down this SR flip flop. Okay. And after that, depending on this output, so it decides whether it will go for a up count or it will go for a down count. Please understand the difference, right. Earlier, if it was up count, then it is going on up counting and then coming back to 0, again it continues to up count, right. Here, every time in every clock, it looks at this comparator output, and based on that, okay, it decides whether this count up will be high and count down will be low or the other way. Okay. So, that is the logic that you can find out here. Is it clear? Okay. So, one shot output, this is 1, it is going to reset. So, it will get reset, after that it becomes 0, and after that, depending on whether this one is high 1 0 or this one is 1 0, depending on that, this up or down, one of them will be high and this will be the count up or count down, one of these two. Okay. So, next clock again a fresh decision is made, right. So, that is what you can see. So, this is up count is happening, and then again it is down count is happening based on this flip flop value, and every time the clock is coming over here and it is continuous lapping. So, this counter is not getting reset. Is it clear? And this is the DAC output and this is the final digital output. So, for continuous conversion, so this is what you would see happening for the input voltage and the analog input voltage vis-a-vis the ladder voltage, that is the digital to analog conversion of the counter value that is there. So, how they map each other. So, this is what you would see for a continuous type conversion. Okay. So, this is the change and this is the corresponding change is over here. So, it is higher value. So, it is going up, here it is coming down because it is lower value. Okay. So, this is the way things will move, right. And this converter of this in this particular converter, the digital output tries to track the analog input, and for which it is also called analog to digital converter tracking type. Okay. So, once it is locked, okay, it is very fast, right, compared to the basic counter based method we discussed before. Okay. So, once it gets locked to the analog input voltage, so either it is going up or coming down. So, smaller number of clock cycles are required. It does not need to begin from 0 for the basic method. Okay. Now, there are certain additional things that goes into this kind of analog to digital converter where continuous conversion is employed. So, it may oscillate when the ladder output is within 1 LSB of the analog signal. So, either it is going up or it is coming down in comparator output. So, it will always oscillate. Okay. So, to avoid that, special arrangement is made, okay, that when the up output such that the up output will not be high unless ladder voltage is more than half LSB below the analog signal. Okay. So, this is something that is included in the circuit in addition, right. So, this avoids oscillation, and similarly for the down output generation. Okay. So, the same thing is done, okay, right. And another issue one often one particular ADC is used, okay, for multiple inputs is there, multiple input is there, and we are trying to convert them, okay, sequentially, right, in a multiplexed manner. So, in such a case, in such situation, this kind of conversion is not suitable because it comes out of the locking, right. Once it is locked, it is very fast. So, every time it has to go through these transients, okay, this the fresh conversion starts. So, that is where it is not suggested. Okay. Finally, another important thing that comes with this kind of A to D conversion as additional circuitry, that when the up count has reached the highest value, that all ones are there, right, all ones are there, okay, like this, right, and still the analog voltage is more, okay, then it will try to go again further. But if the counter goes further, then it will go to all 0, isn't it? So, at that time it should not, it should remain at that value only. Okay. So, that is what is ensured by putting this additional circuit, no up count when all 1 are reached, okay, right, no further up count, and similarly no further down count when all 0 are reached, okay, where you are putting in this case all inverted outputs, complementary outputs, okay, of this thing, and to reset side of the down flip flop, and here it is all uncomplemented to the reset side of the up flip flop. Is it clear? Okay. So, with this we conclude what we have seen very briefly, that simultaneous method of A to D conversion requires a bank of comparators and an encoder to convert the comparator outputs to its digital equivalent. Okay. Flash converters are useful for flash converters uses simultaneous conversion. It is fast, but it requires large number of comparators. So, for n bit it requires 2 to the power n minus 1. Okay. Counter based conversion is simple, the basic one that we have seen, that only one comparator is required, but it requires more time. Okay. So, we move to continuous tracking type converter using counters, which requires both up and down counter and little bit of additional circuitry, and when it is locked to the input voltage, it is very fast. Okay. And for but multiplexed input, it is not advisable, and in the additional circuitry we also include count limiting gates when the analog input exceeds the highest value both in positive and negative directions. Okay. Thank you.